In this video, we're going to talk about the law of cosines. So we're going to start by giving a formula for the law of cosines. So the way I want you to think about this is for right triangles, we have the Pythagorean theorem, which we can use to find all of the sides. As far as our oblique triangles, which we introduced with the law of sines, we can't use the Pythagorean theorem because it only works for right triangles. So for right triangles, we have Pythagorean theorem. But in this section, we're going to deal with oblique triangles. So that's where the law of cosines comes in. So if you notice, it actually looks really similar to the Pythagorean theorem. We have the same formula sitting there, but then we have this extra term added on to it. Okay? So you can rewrite this formula in a couple different ways depending on which sides of the triangle you're dealing with. So another way we could write this is with side B on the other side, and that's going to be a squared plus c squared minus 2ac cosine of b. And then we could also have a squared is equal to b squared plus c squared minus 2bc cosine of a. So once again, all three of these are exactly the same formula. I'm just showing you a few different ways the different things could be labeled. So that is one way that it's a little bit different than the Pythagorean theorem, is that with Pythagorean theorem, remember that the hypotenuse always has to be on that variable c, whereas your two legs always have to be the variables a and b. However, with law of cosines, that is not the case. So the thing on the left side, so this A, B, or C here, just has to correspond to the angle over here. All right, other than that, that's really the only rule for plugging things into this formula. One other thing that's really important when you use the law of cosines is you want to solve for angles in order from smallest to largest. And you want to do this because if you don't, then you could fall into one of those cases like with the law of sines where we could get two different triangles for the same information. So solving things in order from smallest to largest avoids those cases. So make sure you remember to do that. So let's jump in and do a couple of examples. So in this first example, we're going to solve for either x or theta. And in this case, I have the variable x, so that's what I'm going to solve for. So let's see what I have. So I have side C, which is across from angle C. I have side B, which is across from angle B. And I'm looking for side A. So X is that missing side A. So I can use the version of the law of cosines that has A squared is equal to B squared plus C squared minus 2BC cosine of A. And we can just plug in all of the necessary information now. So A is just x in our problem. So we have x squared is equal to b squared. B is 8, so we have 8 squared plus c is 2. So we have 2 squared minus 2 times 8 times 2 times the cosine of 88 degrees. And notice that most of the angles in this section are going to be in degrees, so we want to make sure that the calculator is in degree mode. So I'll make a little note of that up here. All right, so from here we can just simplify this a little bit. So we know that 8 squared is 64, 2 squared is 4, and then 2 times 8 times 2 is 32, cosine of 88. So at this point you want to be a little bit careful. So what a lot of people want to do is just combine these three numbers right here. But you have to be really careful because that third number, so in our case the 32, is multiplied by cosine of 88 degrees. So the only two numbers we can actually combine here are the 64 and the 4. So we get 68 minus 32 cosine of 88. And finally, we can square root both sides, so we get x is the square root of 68 minus 32 cosine of 88. And so that's exactly how you would want to type it in the calculator. So for those of you that might be using a scientific calculator, you'll want to put parentheses around this part that's under the square root to make sure that all of those pieces of what you're typing in actually stay under the square root. Some of the graphing calculators, you may have to do that as well. If you have a super fancy graphing calculator, some of them don't require it, so just be familiar with how your calculator works. Okay, so if we type this into the calculator, we should get that x is roughly 8.18. All right, let's try another example. So in this one, we're solving for theta instead of x. So we've got this missing angle C right here. So let's see what we're given. We're given all three sides. So we have side B is 10, side A is 12, and side C is 20. So since I'm looking for angle C, I'm just going to use the version of the law of cosines where angle C is in the formula, but it really doesn't matter as long as you can plug in all of your information into the correct spots. So for me to keep all of my variables straight, I'm just going to use the version with the angle C. So we'll have C squared is equal to A squared plus B squared minus 2AB cosine of C. So now let's plug in our information. So side C is 20, so we'll have 20 squared is equal to 12 squared plus 10 squared minus 2 times 12 times 10 times the cosine of theta. So our angle C, they're calling theta, so we're just going to put that in there. And now I can start to simplify. So 20 squared is 400, and that's equal to 144 plus 100 minus 240, I believe is 2 times 12 times 10, and then we have cosine of theta. So once again, I can combine the first two terms, but I can't combine those with the negative 240. So I'm going to get 400 is equal to 244 minus 240 times cosine theta. And now I can move the 244 to the left side. So 400 minus 244 gives me 156 is equal to negative 240 cosine of theta. And now I can divide by that negative 240. So we have cosine of theta is equal to 156 over negative 240. And finally, to get theta, I can take the cosine inverse of both sides. So we have theta is cosine inverse of 156 over negative 240. And if I were to put that into the calculator in degree mode, I would get approximately 130.5 degrees. Okay, so those are some basic examples to warm us up for how the law of cosines works. Now let's try one that's a little bit tougher. So we're not going to be given a picture this time. So we want to find the measure of each angle of a triangle with sides 8 foot, 19 foot, and 14 foot. So let's go ahead and draw a triangle, and I'm going to try and make this a little bit to scale so that it makes sense. So we've got one long side here, one long side here, and a shorter side here. So this is going to be 8, and that's going to be angle A because it's across from it. We're going to have side B is the longest, so that'll be over here, and so angle B will go over here. And then we have 14, so this must be angle C. Alright, so this is our triangle, and notice it's not a right triangle. We don't know anything about that, so we definitely need law of cosines. We can't just use, well, we couldn't use Pythagorean theorem anyway because we need to find the angles. So let's see what we can do first. So remember the other caveat here that we want to solve for angles in order from smallest to largest, and that's actually going to correspond to solving or using the sides in order from smallest to largest. So like side A is the smallest, so that's going to correspond to angle A also being the smallest. So that's the one we're going to find first. So first, we're going to solve for angle A. So I'm going to use the version of the law of cosines with angle A. So we have A squared is equal to B squared plus C squared minus 2BC cosine A. So if I plug in my information, I get 8 squared is equal to 19 squared plus 14 squared minus 2 times 19 times 14 times the cosine of A. And continuing to simplify, I get 64 is equal to 361 plus 196 minus 532 cosine of A. And now I can combine the first two numbers and get 64 is equal to 557 minus 532 cosine of A. I can subtract over the 557, and that's going to give me negative 493 is equal to negative 532 cosine of A. So cosine of A then must be negative 493 over negative 532. And finally, I can take the cosine inverse of both sides to get A is equal to cosine inverse negative 493 over negative 532. And that's going to be about 22.08 degrees. So this is my first answer for angle A. Now the second biggest angle is going to be angle C, because the next biggest side is that 14 on side C. So the next one I'm going to solve for is angle C. And we actually don't need the law of cosines again. This time we can use the law of sines. So let's think about why this is. So I found angle A, which I know is roughly 22 degrees. So I'm just going to write that in there since I don't have a lot of room. So notice what we have now is we have a side paired with an angle. So before we had none of the angles, now we have a pair of a side and an angle. So this tells us that we can use the law of sines. So we have that one pair, we definitely have another one of the sides, and we can pair that with angle C. So the way we can set this up is we can say sine of 22.08 degrees over 8 is equal to the sine of angle C over 14, which is the length of side C. So now we can solve for angle C. So we can multiply the 14 to the other side, and we get sine C is equal to 14 sine of 22.08 all over 8. So I can solve for C by taking the sine inverse of both sides. So I'll get sine inverse of 14 sine 22.08 degrees all over 8. And if I were to put this in the calculator, I would get that angle C is roughly 41.13 degrees. So this is my second angle. And then finally I can solve for angle B. And the way I can do that is, well, I have two of the angles of my triangle, and I know that all three of them have to add up to 180. So I can say that angle B is equal to 180 degrees minus 22.08 degrees minus 41.13 degrees, and that's going to give me roughly 116.8 degrees. So that is the measure of angle B. Okay, so this next one, we're going to do something a little similar, but instead of having all three sides, we're given two sides and an angle. So the first thing we should do here is make sure that we don't fall into the ambiguous case that we can get with the law of sines. So remember, that's if you have two sides and an angle that's not between the two sides. In this case, though, we have angle C and we have sides A and B. So on a triangle, this would look something like this. So we'd have angle C and then we'd have sides A and B. So this setup is okay because the angle is in the middle of the two sides. So this is actually going to be a side angle side case. So that would be like the SAS from the law of sines, and that's not ambiguous. So that's good. Okay, so check that off, and that's just kind of off to the side. So we can assume that there's only going to be one triangle in this problem. So we can go ahead and draw it. So I'm just going to draw an arbitrary triangle, try to make all three sides look different, and we can label these as follows. So this one we can just call side A, and then we know if this is angle C, then it must be 75 degrees. And then so that makes this angle B, and the side B would be down here, and that would be 34. Okay, so remember that solve the triangle means to find all three sides and all three angles. So down in the corner here, we're just going to make our little answer box so we can keep track of all the things that we need to find. So we have our three sides, our three angles, and we can go ahead and write in the things that we know. So we know side A is 19, side B is 34, we're about to figure out side C, and then we do know the one angle C is 75 degrees. Alrighty, so let's start by finding the missing side. So first, I'm going to find side C. So to do that, I can set up a law of cosines. I can say C squared is equal to 19 squared plus 34 squared minus 2 times 19 times 34 cosine of 75 degrees. And simplifying this slightly, I'll get C squared is equal to 1,517 minus 1292 cosine of 75 degrees. And then I can square root both sides to get that C is the square root of 1517 minus 1292 cosine of 75 degrees. So if I were to plug this entire expression into a calculator, I would get that C is approximately 34.4. So I'm going to go ahead and write that in the box. Okay, next we can find the two missing angles. So what I'm going to do is I'm going to try to solve those in order as best that I can. So I know that angle A is going to be smaller because the side opposite angle A is smaller. So I'm going to solve for that one first. So second, we're going to solve for angle A. And now that I have the pair side C with angle C, I can actually use law of sines to do this. So we can say that the sine of 75 degrees over 34.4 is equal to the sine of angle A over 19, which is the length of side A. So if I want to solve this for angle A, I'm going to get sine inverse of 19 sine of 75 over 34.4. And putting this in a calculator would give me roughly 32.2 degrees. So we can put that in our box. So we have 32.2. All right, and then third, we can solve for angle B. So again, now that I have two angles of my triangle, I know that all of them need to add up to 180. So I can say that B is 180 minus 32.2 minus 34.4, and that will give me roughly 72.8 degrees. Okay, and that answer makes sense because notice that it's about the same measure as angle C, so they're both really close, and the lengths of side C and side B are really close to each other. So that's good. We can say that these numbers make sense. So now we've solved that triangle. So let's try something a little different now. Now I'm going to give you a triangle, and we're going to solve for either x or theta again, but now you have a choice of whether to use the law of sines or the law of cosines. So in looking at the picture, you're going to have to determine for yourself which one is the better method to use. So for this first one, let's see what we're given. We have a side over here, which is going to be side B. We have angle A, and we have side C. So we're missing side A, but we have angle A. So I don't think that law of sines is a good candidate here because we don't have a pair of an angle with its corresponding side. So we're going to go ahead and use law of cosines, and since we have angle A, I'm just going to write down the version where A is the angle. So let's see what this gives us. So we get A squared is equal to B squared plus C squared minus 2BC cosine of angle A. And now we can plug in all of our information. So side A is what's being called x. So we have x squared is equal to 10 squared plus 18 squared minus 2 times 10 times 18 times the cosine of 40 degrees. So I can simplify this a little bit to get x squared is 100 plus 324 minus 360 times the cosine of 40 degrees. And finally, I can add the first two terms together. So we get x squared is 424 minus 360 cosine of 40 degrees. And now I can square root. So we finally have x is equal to the square root of 424 minus 360 times the cosine of 40 degrees, which if we put that into a calculator, that turns out to be roughly 12.2. So that's the length of our missing side x. Now in this next example, you'll notice that the setup is a little different. So let's determine whether law of sines or law of cosines would be better to use. So we're given all three sides, and we're missing an angle. So remember, for law of sines, what we're looking for is if we have a side and an angle pair. So for example, I might have angle B and side B. But in this case, I don't have that because B is actually the angle that I'm looking for. So I think law of cosines will be better again here. So we're looking for angle B, so I'm just going to use the version with B as the angle. So we'll have B squared is equal to A squared plus C squared minus 2AC cosine of B. So side B is 4, so 4 squared is equal to 10 squared plus 11 squared minus 2 times 10 times 11 times the cosine of theta, because that's what we're calling our missing angle. So we get that 16 is equal to 221 minus 220 times the cosine of theta, and I can subtract over the 221 to get negative 205 is equal to negative 220 times the cosine of theta, and now I can say cosine of theta is equal to negative 205 over negative 220, which in turn I can take the cosine inverse of both sides to get that theta is the cosine inverse of negative 205 over negative 220, which if I were to put that into a calculator, I should get roughly 21.3 degrees. So that is the answer to this example. So those were some basic examples with the law of cosines. Mostly I either gave you pictures or I gave you some given information about a triangle and expected you to draw the picture. What we're going to do now is kick things up a notch and try to do some word problems. So in this first example, we're going to be talking about Little League baseball fields. So according to Little League regulations, the diamond is a square 60 foot per side. The pitching rubber is located 46 feet from home plate on a line joining home plate and second base. So maybe before we start trying to get into the questions, let's just draw what this baseball field looks like. So we've got a square, and it's in the shape of a diamond, so I'm going to draw it diagonally like this. And so we know a square has right angles at all the angles. And we're being told that it's 60 feet per side. So each of these sides is 60 feet. And so each of these angles, I'm just going to label with letters to tell us like which part of the baseball diamond it is. So home plate will be the bottom one. First base will be on the right there. Second base will be at the top. And third base will be on the left. And the pitching rubber is located 46 feet from home plate on a line joining home plate and second base. So we're going to draw a straight line connecting home and second. And the pitching rubber is located somewhere in the middle where it's 46 feet from home. So it might look like that. So now let's turn to our questions. So our first question is, how far is it from the pitching rubber to first base? So what we're looking for in part A is the length from pitcher's mound, which is in the middle here, to first base. And so the way I've drawn this picture might make you think that we're drawing a right triangle, but we're really not. So keep that in mind. We cannot assume that these triangles are right triangles. So in part A, we're going to be talking about the triangle that I just highlighted in yellow. And we want to find the length of this side right here. So maybe I'll call that side X. So for part A, we need to find side X. And so let's see what I can get from this triangle. So maybe I'll redraw the triangle so that it's a little bit more clear. All right, so we have home plate down here. We have first base over here. We have the pitcher right here. And so let's label what we can on this triangle. This side we know is 46 feet. This side is 60 feet. And then I want to find this side here, but in order to do that, I'm going to have to know at least one of these angles. And I think the one we should know is this one down here by home plate. So what happened was when we drew that straight line from second base to home, we actually cut that right angle in half. So the angle from this 46 line to this 60 line is really 45 degrees because we cut that right angle exactly in half. So now I have a triangle that looks very similar to the examples I've already done with the law of cosines. So what we can do is just use law of cosines to get x. So let's set this up. So we can say that x squared is equal to 46 squared plus 60 squared minus 2 times 46 times 60 times the cosine of 45 degrees. And now I can simplify a bit and say x squared is equal to 5716 minus 5520 times cosine of 45. And I can square root that to get x is equal to the square root of 5716 minus 5520 times the cosine of 45. And if I were to put that into a calculator, I should get x is roughly 42.6 feet. So that's my answer for part A. Now part B, let's see what we want to find. We want to find how far is it from the pitching rubber to second base. So in part B, we're looking for this distance right here. So there are a couple of ways you can do this. The way that I'm going to do it is by using this bigger triangle right here. Let me highlight this. We can see what it looks like. So for part B, I'm going to use the entire half of the field, which is this triangle right here. So let's try to do part B. So I'm going to redraw that triangle just so we have less chaos on it. So it's going to go like this. We know that each of these two sides is 60. We know that this is a right angle, and we know that the pitching mound is located here with a line going to first base. And we also know that this is 46, and this is the side that we're looking for. So I'm just going to call that x again. All right, so we could have set this up in another way where we used law of cosines, but I think that this way is slightly easier. Because what I'm working with here is a right triangle because I have that right angle at first base. So I'm looking at a right triangle where I know two of the sides, but I still need to find the third side. And to do that, I can just set up a Pythagorean theorem. So it's not really necessary to use law of cosines because I already have a right triangle. So Pythagorean theorem will work just fine here, and we can set this up as follows. So we have c squared is equal to a squared plus b squared. So the two sides of length 60 are playing the roles of a and b. So we'll have 60 squared plus 60 squared on the right. And on the left, that side c is going to be the sum of 46 and x. So I'm going to have 46 plus x, or actually let me write it the other way around. We'll have x plus 46 squared. So now what I can do is I can expand this all out and try to solve for x. So if I do that, I get x squared plus 92x plus 2,116 is equal to 7,200. So now what I have is a quadratic equation. So to solve for x, the first thing I need to do is get everything on the same side. So I'm going to get x squared plus 92x minus 5,084 is equal to 0. And once I have that, I can use quadratic formula. So I'm not actually going to solve the quadratic, if I can spell this correctly, quadratic formula. So I'm not going to work out the quadratic formula because I hope that you've remembered that from college algebra, and I don't want to spend time in this video with that. But if you're unfamiliar with it or a little rusty, be sure to come and see me during office hours and I will go through all the steps. So if you use quadratic formula, we get that x can either be 38.85 or x is equal to negative 130.85. So quadratic formula is always going to give you two answers, but a lot of times one of those answers won't make sense. So in this case, we got 38.85 and negative 130.85. So this negative answer down here doesn't make sense because it's negative, and we're talking about a distance. So distances are never measured in negative feet or negative inches or anything like that. So we always want to go with the positive answer when we're talking about a distance. So I should actually say 38.85 feet, and that will be our answer for part B. Okay, now let's look at part C. So if a pitcher faces home plate, through what angle does he need to turn to face first base? So what we're looking for in part C is we're looking for the angle right here. So we want to know what is the angle from the pitcher facing home plate to the pitcher facing first base. So we're going to be working with the same triangle from part A, except we're going to be looking for this angle here. All right, and so let's see how we can do that. So because I've already solved part A, I now have this pair of angle C with side C. So I've got that angle C across from that side of length 60. So what I can do is I can actually set up a law of sines. So you could use law of cosines, but it's not necessary. So let's set up a law of sines. So we're going to have sine of angle C over 60 is equal to the sine of 45 over that side that we found from part A. So that was 42.6. And now I can just solve for angle C. So I'm going to get that angle C is the sine inverse of 60 times the sine of 45 divided by 42.6. And if I were to put this into a calculator, I'd get that angle C is 84.8 degrees. All right, so that is the Little League problem. So the next type of application we're going to talk about is a little more complicated, and it's probably something that you're not super familiar with. So that's why I'm going to make sure I go over this in depth. So what we're going to talk about is what we call bearings. And bearings are basically a way for people to navigate on ships. So it's basically a unit of measurement that involves your four cardinal directions, north, south, east, and west, and certain angles from those directions. So a bearing measures the acute angle a path or line of sight makes with a fixed vertical line. So I have a little picture here at the top that sort of gives you a couple of examples. So what's going to happen here is we're going to choose a direction of either north or south, and then we're going to move some angle away from north or south in either the east or the west direction. So this first one up here says north 45 degrees east, and this one at the bottom says south 45 degrees west. So the important thing to notice is that we're going up or down first, and then we're going right or left, which is a little different from what you're used to doing on coordinate planes where we always say x coordinate comes first, then y coordinate. Now we're going basically the y direction first and then over some or around some x angle, I guess is some way to think about it. So for example, if we were given the bearing north 30 east, we're indicating a direction that points 30 degrees to the east of north. And some of the examples you see in your homework might switch between the bearing notation, which is like this, and actually writing out east of north or west of south or east of south. So be familiar with the differences between those. They're talking about the same thing, they're just written a little bit differently. So let's try an example of a problem. So a ship leaves port at noon and heads, excuse the typo there, and heads due west at 20 knots, which is the same as nautical miles per hour. At 2 p.m., the ship changes course to north 54 west. Find the ship's bearing and distance from the port of departure at 3 p.m. So that was a lot to digest in the problem. Let's start by drawing a picture. So let's say that the ship starts at this port and heads west. So west is going to be to the left. So we're going to start with an arrow going this way. Maybe I should shorten that a little bit. Okay, so let's say that's where the ship initially goes. Then at 2 p.m., we're going to change course to north 54 west. So be really careful when you're drawing these pictures, because remember with bearings, we're always talking about an angle from the vertical. So we don't want to start with the horizontal and get some angle up here. We want to start with the vertical, like I have drawn here, and we want to go some angle this way. So what we're going to do is go north, that's why I've drawn the line going up, and we're going to go 54 degrees to the west, which is in the left direction. Alright, so we've got another arrow going this way, and this angle here is 54 degrees. So we want to find the ship's bearing and distance from port of departure at 3 p.m. So this final dot all the way to the right is going to be 3 p.m. This is the first dot is noon, and the middle dot is 2 p.m. So the distance is going to be the straight line from the final dot to the initial dot. So this is going to be the distance. And the bearing is going to use the angle from the vertical line at port to that distance. So this here is going to be the bearing angle. All right, so now that we have that in mind, let's get to work. So one problem we have here is we're given a speed, but we're not given distances. So in order to solve for any side on this triangle, we're going to need to find out how long the sides of this triangle actually are. But we are given a speed and we're given a time, so we can use that to actually get the distance that the ship has gone in each time period. So first we're going to do from noon to 2 p.m. So from noon to 2 p.m. we're going 20 nautical miles, which we abbreviate with NM, per hour, and we're going to do that for 2 hours, from noon to 2. So we can convert this by multiplying it by 2 hours. Our hours are going to go away, and we're left with 40 nautical miles. So between noon and 2, we went 40 nautical miles. So this bottom side of the triangle is going to get a label of 40. Now if I want to find the length of the other arrow, what I can do is say from 2 p.m. to 3 p.m. We never said we changed speed, so we're still going 20 nautical miles per hour, but this time we're only going for 1 hour, so we're just going to be 20 nautical miles. So this side on the left is going to get a label of 20 nautical miles. So now I have two sides of my triangle, and I have this angle of 54, but that's not quite the angle of the triangle. However, I know I have a vertical line and I know I have a horizontal line, so this angle in here must actually be 90. And using that, I can get the total angle of that triangle. So let's actually get what we have here. So we now have a situation where we can use law of cosines. We have two sides with the angle between them, and we're looking for the side across from that angle that we have. So if I set up law of cosines, I can say x squared is equal to 20 squared plus 40 squared minus 2 times 20 times 40 times the cosine, and I'm going to have to add 90 to 54, and that's going to give me 144 degrees. So just a little note, maybe I'll put a star by that and say, or you know what, maybe I'll highlight it. So if I get my highlighter, we can say 144 is equal to 90 plus 54. All right, so that's where that came from. Okay, so now this is just like any other law of cosines problem that we've done. So we can go ahead and start simplifying. We get that x squared is 400 plus 1600 minus 1600 times the cosine of 144. And if I keep going, I'm going to get that this is 2000 minus 1600 cosine of 144. I can take the square root to get the square root of 2000 minus 1600 times the cosine of 144. And then finally, if I were to put that into a calculator, I would get that x is approximately 57.397 nautical miles. So that is our distance. Now, I also need to find the bearing, which involves finding the angle, and then I know that it's going to be north and west are my two directions because I see that this line here is going up and to the left. So I know that my two directions are north and west, but I still need to find that angle. So let's think about how we can do that. Well, maybe I can't find that angle right away, but I could find this angle right here. I could find the angle between the west line and the distance line. And that shouldn't be too bad because I have this angle here, and I now have my distance, so I have a pair of a side with an angle, and then I also have the side across from the angle I'm looking for. So what I have here are two pairs of an angle with its corresponding side opposite the angle. So what that tells me is I can actually set up a law of sines to find that red angle that I highlighted here. So what I'm going to say is I'm going to say that the sine of 144 over 57.397 is equal to the sine of, I'm going to call it angle P for port, just so we remember what we're talking about, over 20. So that's my law of sines. Now to solve for angle P, I can say that this is sine inverse of 20 times the sine of 144 degrees over 57.397. And if I solve that in the calculator, I should get that angle P is approximately 11.819 degrees. But when we're talking about bearings, we always want to round to the nearest degree. So we're going to say that this is about 12 degrees. So let's see what we can do here. So I've found the red angle, but I still need to find that blue angle from vertical. So I know that my westward line and that dotted vertical line again make a 90-degree angle. So to find the actual bearing angle, we need to do 90 minus 12, which would give me 78 degrees. So what we get is that our actual bearing is going to be north 78 degrees west. So notice here that even though we found an angle, that wasn't our actual answer. Our actual answer was the bearing written in bearing notation. So we had our two directions that sandwich this angle that we found. All right. Let's try another one dealing with bearings because I think that's probably the hardest types of word problems for people to get. So in this example, we have an airplane flies due north from Fort Myers to Sarasota. So we're talking about some towns in Florida here. A distance of 150 miles and then turns through an angle of 50 degrees and flies to Orlando, a distance of 100 miles. How far is it directly from Fort Myers to Orlando, and what bearing should the pilot use to fly directly from Fort Myers to Orlando? So just like we did with the previous problem, let's start by actually getting a picture of what's going on. So we have the airplane starting at some point down here, and it's flying due north. So down here we have Fort Myers. Up here we have Sarasota. And then, well, let's see. This will not fit on the page, so let me make this arrow a little shorter. So maybe it's right here. We have Sarasota. And then what's going to happen is the plane is going to turn through an angle of 50 degrees. So that's kind of a nice way of saying a bearing. So what that means is we're going to start at the vertical and we're going to go 50 degrees around like this. So this angle is 50 degrees and it's going to end up at Orlando. So our picture looks like this, and we also know how far each of these sides is. So from Fort Myers to Sarasota, we were told it was 150 miles, and from Sarasota to Orlando, we're told that it's 100 miles. So these two sides get 150 and 100 respectively. So now question A is saying how far is it directly from Fort Myers to Orlando? So this is sort of like the distance that we found in the previous problem. We want that straight line from Fort Myers to Orlando that completes the triangle. So let's see what we can do. So we're looking for this side in part A, and so I guess my question is, if I want to use law of cosines, do I have this angle right here? And I think I do. I claim that I do because I have this angle of 50 degrees, and I see that that angle of 50 degrees and this angle that I'm looking for lie along a straight line. So we've got this situation here. And those angles must add to 180 because they make a straight line. So this angle must be 130 because 180 minus 50 gives me 130. So now I have a situation where law of cosines is going to work out really nicely. So I can say that x squared is equal to 100 squared plus 150 squared minus 2 times 100 times 150 times the cosine of 130 degrees. So simplifying this a little bit, we get that x squared is equal to 32,500 minus 30,000 cosine of 130. And I can take the square root and get square root of 32,500 minus 30,000 cosine of 130. And finally, the calculator should give us that this is about 227.56 miles. So this is part A, and that's my answer to part A. Maybe I should label the part up here. So this is part A. So now part B says, what bearing should the pilot use to fly directly from Fort Myers to Orlando? So if they're asking for a bearing, we know that we need an angle, first of all. So the picture actually sets up our angle kind of nicely because we're dealing with vertical lines. And so basically what we're going to want here is this angle right here, between the vertical line and that distance line from Fort Myers to Orlando. So let's think about how we can find this angle. So now that I've solved part A, I know this distance line is 227.56. So notice what I have is I have the angle that pairs with that side, and then I also have the side that pairs with the angle I'm looking for. I have the side labeled 100 with the angle at Fort Myers. So what this tells me is I can actually set up a law of sines. So I'm going to set up the sine of 130 over 227.56 is equal to the sine of, I'm going to call it F for Fort Myers so we don't forget what we're talking about again, and the side length there is 100. So now I can solve this pretty easily. I can just say that the angle F is equal to the sine inverse of 100 sine of 130 over 227.56. And putting that into the calculator should give me that F is approximately 19.67 degrees, which with bearings, remember we want to round to the nearest degree, so we get that that's about 20 degrees. So my final bearing, I notice that I'm going up and to the right, so my final bearing is going to be north 20 degrees east. And so that is my answer for part B. So hopefully the applications weren't too scary for you, but again, if they're confusing or you have any trouble at all, please come see me in office hours. So the last thing that we're going to talk about in section 8.2 is another way to find the area of a triangle. So remember in 8.1 we did the method where we used the height to get a formula that's really closely related to the one that you probably remember, the 1/2 AB was the area formula, and we just plugged in the height for one of those sides. Or actually, no, I'm sorry, not AB. Base times height, 1/2 base times height. So we basically found an expression for the height that used the sign, plugged it in, and that gave us a new formula. This one's a little different. So this is what we call Heron's formula. So I think Heron was an ancient Greek mathematician. He's a really old guy. But the point is he came up with this way of finding the area of a triangle that uses the side lengths. So we never actually talk about an angle at all. We're just going to use all three sides. So the formula that Heron came up with was he said the area is equal to the square root of S times S minus A times S minus B times S minus C, where S is something that we call the semi-perimeter, which is 1/2 A plus B plus C. So this is what we call the semi-perimeter. So perimeter just means the distance around a shape. So if we're talking about the triangle, we're just going to add up all three sides. And semi tells you that you want half of that. So we're literally just taking half of the perimeter. And so we're going to use that semi-perimeter in the area formula. So let's try an example. So we want to find the area of a triangle having sides A equal to 43 meters, B equal to 53 meters, and C equal to 72 meters. So to find the area, well, first of all, on a test, I wouldn't tell you which formula to use to find the area. I would be fine with whichever method you want. But given certain situations, you should be able to notice that certain formulas would be better than others. So if you're given all three sides, Heron's formula is a great way to find the area of the triangle. So that's what we're going to do here. So the first thing I need to do to use Heron's formula is to find the semi-perimeter. So S is going to be 1/2 of all three sides added together. So we're going to have 1/2 of 43 plus 53 plus 72. And that should give me 84. Now that I've found the semi-perimeter, I can find the area. So the area is going to be the square root of the semi-perimeter times the semi-perimeter minus side A times the semi-perimeter minus side B times the semi-perimeter minus side C. So if I plug in all the numbers I have, I know that S is 84, so I'm going to have 84 times 84 minus 43 times 84 minus 53 times 84 minus 72. And now I just have to be really careful when I simplify. So I'm going to get the square root of 84 times 41 times 31 times 12, which is going to give me the square root of 1,281,168. And if I take the square root, that's going to give me approximately 1,131.9 meters squared. So just remember that when we're talking about area, we always take the distance unit that we had in our problem, which in this case was meters, and we're just going to square it because now we're talking about a two-dimensional measurement of area. So this is going to be the area of my triangle. So that concludes our law of cosines lesson.